Hello, this is Alan Elliott, and this is SAS Essentials, Mastering SAS for Data Analytics, 3rd edition. This is Chapter 11, Analyzing Counts and Tables. In this chapter, we will learn how to use PROC FREQ to create one-way frequency tables. Also, using PROC FREQ, we'll create two-way cross-tabulation tables. We'll also look at how to use 2x2 contingency tables to calculate relative risk measures and to be able to use Cohen's Kappa to calculate inter-rater reliability. As usual, if you'd like to follow along with examples, please download the files at this location. Let's begin. Let's look at section 11.1, using PROC FREQ. PROC FREQ is a multi-purpose SAS procedure for analyzing count data. In the previous chapter, we looked at PROC means and PROC univariate to analyze continuous numeric data. So this is count data instead. It can be used to obtain frequency counts for one or more individual variables or to create two-way tables, such as cross-tabulations from two variables. A simplified syntax is as follows. It follows the normal procedure for a PROC, so PROC FREQ, followed by options and a semicolon, then statements. In this case, we have something called tables and the requested tables, and then /options. There's a lot of options and statements covered in this chapter, so I'm not going to go over all of them, just some things that maybe are unique to PROC FREQ. For instance, the page option here specifies that only one table appear per page. Now in HTML this doesn't have any effect since everything appears right after one another. Alpha sets the confidence limits. We've seen that before. Compress begins the next table on the same page when possible. Again, not HTML. And then we've seen no print before. Common statements for PROC FREQ includes exact, which produces exact p-values for tests such as Fisher's exact test. Output we've seen creates an output data set. Weight we've seen in the past identifies a weight variable that contains summarized counts. Tables is a specific statement for PROC FREQ that we'll use over and over again. It's a very important part of PROC FREQ, and it specifies which tables will be displayed. We'll look at that as we go along through the examples. Test specifies which statistical test will be performed. Again, we'll see some of that later. And then by format label and where we've seen before. So the table statement, as I mentioned, is very important. It's required for all of the examples in this chapter. And the format of it is tables and then whatever variable combinations you're looking for /options. So in the example below here, I have tables A by B or A times B, whatever you want to call it. A and B are both variables, so it could be height by weight or length by width or something like that. And then, so that specifies the tables. You want counts for, so A and B are both count type variables. And then /chi-square specifies which kind of analysis you want for this table. All right, to obtain some counts of the number of subjects observed in each category, like group, we can simply use PROC FREQ tables group. That's a one-way table. We're simply going to give us the number of subjects that appeared in each group, GP. If we want to look at a cross-tabulation of gender by group, then we say tables gender times group or gender by group. Then if we want to add a test to it, we would say tables gender by group /chi-square. Here are some more sample table statements. So again, we looked at tables A, which is just a single variable. Again, A and B are variable names here, just to make it short and simple. Tables A times B or A by B specifies a cross-tabulation of two variables. You can also have ask for many variables, many tables at a time. So tables A times B, B times C, X times Y. Or you can say tables A and then in parentheses B, C, D, which would produce A by B, A by C, A by D. And also you can use the slash slash, so A dash dash C times X would be A times X, B times X, C times X. So those all make sense from what we've seen before. Then some options for the tables. Now I'm not going to go through all of these, and the chapter doesn't, or this, at least this tutorial doesn't cover the meanings of all of these, or examples of all of these, but it does some. The agree option is requests a Kappa statistic. Rel risk requests relative risk calculations. Fisher is the Fisher exact test. Sparse requests all possible combination of the levels. Missing requests missing value be treated as non-missing. Cell chi-square displays the contribution to chi-square. So if you're familiar with calculating chi-square and want to know which cell, how much of the chi-square value is contributed by each cell, that's one way to do it. No column, no cumulative, no freq, no percent, suppresses those various things, so as does no print and no row. And then test P equal list specifies a test based on percentages, and we'll see an example of that. So first let's look at analyzing one-way frequency tables. So when count data are collected, you can use PROC FREQ to produce tables of counts by categories, as well as to perform statistical analyses on these counts. The number and type of tables produced by the PROC FREQ are specified in the table statement. So this section describes how to create tables of counts by category and how to perform a goodness of fit test. So let's do example 11.1. Open up the program file afreq1 and you'll see this code here. And you'll notice here we're going to do a PROC FREQ on a data set we already have called sum data, tables, status. So all this is going to do is give us the counts of how many people are in each status as a socioeconomic status. The second example is the same table's status, but we're going to order it in a specific way, order equal freq. So it's going to order it by frequency. So here's the results. So the first time we say tables status, and it gives us the frequency 3, 7, 6, 8, 26 of the various 5 different status values there. But then if we add the order equal freq before the table statement, it orders it in descending order of the frequency. So 26 becomes the first one, then 4, and then 2, and then 3, and then 1 in terms of the value of status. There are other ways to ask for the ways for it to be displayed using the order option. You can say order equal data, orders values by their order in the data set. Format orders values by ascending values determined by a format statement. We'll see an example of that. Freq that we just saw orders values by descending frequency count, and order orders values by order in the data set. So just as an exercise, change the previous code to say order equal to some of these other ones here. For instance, order equal data, and just see what the difference is. Okay, so one of them that wouldn't have worked in the last, that wouldn't have really had any effect on the last example is the order equal formatted, because in order for order equal formatted to work, you have to have some sort of format to begin with. So we've seen PROC format before, but let's take a look at this. So let's say we have a categorical variable whose values are AA, H, OTH, and C, and we want to call them African American, Hispanic, Other, and White. And what this is going to do, notice that the name C, which maybe was Caucasian, we've changed to the name White, and that's going to order it with W as the last value in this format, rather than C, which would have appeared between African American and Hispanic. So to cause this to take place, we would say PROC FREQ order equal formatted, and then we ask for the table's race, and then we apply the format. Format race, FMT race dot. That applied the format to this data. And so let's take a look at how that would work. So open up the file called afreq2.sas, and here we see the format is created, and then the PROC FREQ order formatted And the arrows there sort of show you where things go. So we created the FMT race format, and it goes in the format statement in PROC FREQ. The race, table's race, is the value that we're going to format using that FMT race format. And here are the results. Again, it's going to order it by the formatted values. So African American appears first, then Hispanic, other, and white. So it's ordered by alphabetized race. All right, now let's take a look at creating a one-way frequency table from summarized data. Now, oftentimes, instead of just having a list of counts where you have a lot of data that represents one person per line, maybe you already have counted some values, and so you know how many of certain things you have. So for instance, here I have some values for coins. I had 152 cents, and maybe I had a couple of rolls, so I also had another 100, 49 nickels, 59 dimes, and so on. So this data then now is going to have these counts in it rather than 152 lines either they say cent. All right, so now let's take a look at how that would work. So open the program file afreq3.sas, and we're going to create the coins data set where we're going to read the category, cents, nickels, etc., and then a number. And this number is going to become our weight variable. We saw this in some previous examples where we had the weight option. So number is how we're going to weight these variables. So when I say table's category, what it's going to do is it's going to look at the category cents and say, aha, there's 152 of them. Whoops, there's also 100 of them. So it'll combine those, as we're going to see. All right, so when we run the program, now we see that it combines cents, 252, then dimes and dollars and so forth, and it gives us the frequency of each. So 56% of our coins were cents, 13 were dimes, about 5% were dollars, and so forth. Okay, let's look at testing goodness of fit in a one-way table. So a goodness of fit test is of a single population to determine if the distribution of observed frequencies in a sample closely matches the expected number of occurrences in a hypothetical distribution. So the null hypothesis is that the population follows whatever hypothesized distribution we have, or the alternative is that it is not. And a goodness of fit test using PROC FREQ is done in this way. So look at the code here at the bottom. PROC FREQ tables whatever variable contains the information we're interested in / chi-square. And then the important thing here is the test p equal statement, and then a list of ratios. Now this is the list of hypothesized ratios that we're interested in comparing. Did what we observe fit in the same proportion as this list of ratios that we're going to list there? So here's an example from a 19th century monk, Gregor Mendel. You may have seen some similar data if you had biology courses in the past. But he took two different types of peas, yellow and green, smooth and wrinkled, and crossbred them, and observed how their offspring. And according to his genetic theory, the plant should show a 9:3:1 ratio. That is, when he crossbred them, he should see 56% yellow smooth peas, 18.75% yellow wrinkled peas, 18.75 green smooth peas, and about 6% green wrinkled peas. So the question is, can he repeat this? Can he do a certain number of plants, observe the results, and see that they did indeed follow this hypothesized proportion? So after growing 556 plants, Mendel observed the following. So this is the actual data he observed, not the hypothesized. So he observed 315 yellow smooth peas and 108 yellow wrinkled peas, and so on. Now, the question is, can we compare what he observed to the hypothesized value and determine whether this observation fit with the hypothesized ratios? And this is how we would do it. So the data is up in the upper right, data gene. I'm reading in color type and number. So yellow smooth had 315 and so on. And then open the program file afreq4 to see this code here where we have PROC FREQ, and we're using that data that we just created. We're going to order the data in the way it came in. That's the order equal data. Weight number means that what we're seeing are counts. And then the tables, color type, that's yellow, smooth, etc. And I'm going to have a slash no cumulative and chi-square. The reason I put the no cumulative option in there is I didn't want to see the cumulative row of information because it's irrelevant to this test. And then we have the test P ratios. And again, that's 0.5, 0.625, 0.81, 0.1875, 0.1875, and 0.0625. I'm going to back up just a couple just to show you that's where they came from. These are the same ratios that we hypothesized earlier. All right, so just to go over that again, so we're using the weight number because we have counts. Order data is going to cause it to come out in the way that the data was created. We're going to use color type as the frequency. We're going to use the no cumulative and chi-square options and the test P statement to request the particular percentages that we're interested in comparing to. All right, so let's look at the results. The top table here are the results. So we notice here frequency column is the actual observed, 315, 108, and so forth. And then 315 was 56.65 of the total. And the test percent, that is what came from test P equal, is 56.25. In yellow wrinkle, we observed 19.42%. We hypothesized 18.75%. And you can see the other ones there. I think it's always a good idea to take a look at the table and visualize whether you think, without looking at the test first, visualize whether you think this test supports the null hypothesis or the null hypothesis should be rejected. In this case, it seems pretty close. The 56, 56, 19, 18, 18, 18, and 5 and 6, it's pretty close to what we expected. And indeed, if you look down at the bottom where the chi-square test is, you'll see the p-value is 0.92, which is far above 0.05. And so we do not reject the null hypothesis and conclude the evidence supports the theory that the population exhibited the 9331 phenotypic ratio. All right, now let's look at section 11.4, analyzing two-way tables. So previously we've only looked at one variable at a time. Now we're going to look at two variables at a time, and we would say something like A by B or A times B, as you see there, where A and B are variables. They're both count type variables. So cross-tabulation is formed by counting the number of occurrences in a sample across two grouping variables. Sometimes you'll also hear people talk about this table as an R by C table, where R is rows and C is columns. So the hypotheses associated with this could be a test of independence as follows. The variables are independent, therefore there's no association between them, or that they're not independent. For example, a null hypothesis could be that there's no association between handedness, left and right-handed, to hair color. Now notice left and right are mutually exclusive. You can either left or right, and hair color is a non-ordered kind of category as well. However, let's look at a test of homogeneity. In this case, we're looking to see if within a population, does it have the same distribution? So the null is the populations are homogeneous or they're not. Now in this case, for instance, let's look at two populations, male and female versus left-handedness. Now in this case, maybe what we're interested in is knowing whether or not the distribution of handedness is the same in males and females, as opposed to whether or not in the previous example there was any association at all. All right, to test this hypothesis, we could use the PROC FREQ and then tables gender by group. That's what you say typically with the little asterisk there. Gender by group and / chi-square. Most of the tests we're doing here is going to be the chi-square test. All right, let's look at some actual data. This is old data from 1909. This was probably one of the original uses of this kind of analysis. And in this case, data were collected from a number of people who were in jail or incarcerated in London and or in England somewhere. And we were interested in knowing whether or not a person being a drinker had some sort of relationship between the type of crime they committed, or for instance, were the same number of, or the same proportion of people drinkers in each type of crime. So here we have arson, where 50 were drinkers and 43 were not. In a rape cases, 88 were drinkers and 62 were not, and so forth. Coining down at the bottom refers to counterfeiting. All right, the way to analyze this data, first of all, we need to realize that we have counts. So we use that weight variable there, weight count. We're looking at the table crime by drinker, and then asking for the chi-square test. And here are the tabled results. Now let's look at the cells. The cells contain 4 numbers. The first is count, then total percent, row percent, and column percent. What we're really interested in is the row percent. So let's look at arson. The row percent is 46 and 53. That means that 46% of the people were not drinkers, 53 were drinkers. In coining, 43% were drinkers, 56 were not, and then we can look at the rest of them. It seems that all of them follow this almost sort of 40% to 50%, 40 to 60% kind of ratio, except for fraud. Notice here it's just the opposite of the rest. It's 69% versus 30%. So again, if we look at this table visually before we actually even look at the chi-square, we can say, well, I'm not sure that the ratio is maintaining across all types of crime. Most crimes look like they were like a 45 to 55% ratio, except for fraud, which is like a 70 to 30% ratio. So let's see what the result is. And not surprising, the chi-square then is less than 0.001, which means we reject the null hypothesis. There's no association, and conclude that there is a relationship between drinking status and type of crime committed. Now, a lot of analyses of what this might have meant, but one of them would be if you're perpetrating fraud, maybe being a drinker is not a good idea because you have to have a clear mind. All right, so that data was count data, as we've seen in the last couple of instances. But now let's look at an example where we're using raw data. In this case, a 2x2 case where there's 2 categories in each variable. In this case, we're looking at cleaners and whether or not someone who used that cleaner experienced a rash. So we have 2 kinds of cleaner, 1 and 2, and rash, yes, no. And so here is the first of our data here. You notice subject 1 used cleaner 1 and did not have a rash. Subject 2 used cleaner 1 but did have a rash, and so forth. And so each subject is one record in the data set. So in this case, we don't have to use the weight statement in our analysis. So here we have the analysis where we have PROC FREQ, we're using rash, tables cleaner by rash / chi-square. So let's take a look at what we get here. And first look at the table on the left where we see cleaner 1 and 2 on the side and rash, yes, no at the top. We see that for cleaner 1, we had 7 people didn't have a rash, 13 did. But in cleaner 2, 16 people had a rash and 4 didn't. And we could look at the ratios there and see it's a 35 to a 65 versus 80 by 20. We see that looks different. It doesn't look like a consistent pattern. And not surprising then, when we look at the chi-square test, we get 0.004, less than 0.05. We reject the null hypothesis and conclude that indeed there is a difference between whether or not you get a rash and which cleaner you use. There's another test we haven't seen yet, but it's called a Fisher's exact test. And this test is sometimes available, particularly in a 2x2 case. Gives us as it says, Fisher's exact test. It's based on a different way of doing it. I won't go into that, but it gets 0.0095, slightly different numbers, but it comes to the same conclusion. Okay, let's look at another way of using PROC FREQ, and that is calculating relative risk. In the 2x2 contingent tables are often used when measuring, examining a measure of risk. A measure of this risk in a retrospective or case control study is called the odds ratio. Now, retrospective means that we're looking backwards in time. So in a case control study, a researcher takes a sample of subjects and looks back in time for exposure or non-exposure. As an example, suppose people got sick at a picnic, and you look back in time to determine what they ate. Did they have the potato salad or the chicken salad or not? If the data are collected prospectively, that is, this is where subjects are selected by a presence or absence of a risk and then observed over time to see if they develop an outcome. So perhaps you observe people who smoke and then follow them over many years to determine whether or not they develop cancer or something like that. This is called a relative risk. Either way, the way we measure it is that either a relative risk equal 1 or an odds ratio equal 1 means that no risk was observed. That is, the same number of people experienced the problem as did not. So in the case of the odds ratio, the same number of people, or it didn't matter whether someone ate the potato salad and whether or not they got sick. All right, so how do we test that? We test it using PROC FREQ. So the PROC FREQ option, the option to calculate the values for odds ratio or relative risk is REL-RISK, rel risk, and appears as shown in the tables option. So instead of the chi-square that we've seen up to this point, we now have rel risk. And again, in the results, if a risk measure is greater than 1, it indicates the exposure to whatever we're measuring is harmful, and a risk less than 1 implies that the exposure is actually beneficial. All right, so let's take a look at how we can measure that. Let's open up the program afreq6.sas. We've previously used it, but in this case we're going to change, we're just going to make one change. Change the chi-square to the rel risk measure there and run the revised program. Now we get the same answers in terms of the table as you can see here, but the difference is going to occur in the analysis, and that is we see that we get a table called odds ratio and relative risk. In this case, typically the odds ratio was a statistic of interest because we were looking back in time to measure that information, and the OR of 0.1346 specifies the odds ratio of row 1 versus row 2. And again, it depends on how you set up the data, but in this case it's for cleaner 1 versus cleaner 2. So we're looking at cleaner 1 versus cleaner 2, and so because OR is less than 1, it indicates that the odds of a person having a rash who is using cleaner 1 is less than when the person is using cleaner 2. So if we go back and look at the data, we can see again that the odds of somebody, or look at cleaner 1, 7 to 13 versus 16 to 4. So again, we see visually that this is exactly the case, that someone using cleaner 1 has less risk than someone using cleaner 2. There's more about this in the text, and I encourage you to follow along there. Now let's look at a different topic, and that is inter-rater reliability, or Kappa. A method for assessing the degree of agreement between two raters is called Cohen's Kappa coefficient. We'll look at what this means here as we go move along. For example, Kappa is useful for analyzing the consistency of two raters who evaluate subjects on the basis of some categorical measurement. So in this case, from a textbook by Fleiss, we have this data where we had two raters, rater A and rater B, and they were both looking at the same subjects, and they were rating people according to some kind of psychological measure, and here we have whether or not a person was experienced a psychological, neuro, or organic issue. And so rater A rated them and rater B rated them, and we want to know is the way that they're rating them consistent, and that is, and this may be doctors or something like that, is the way that they're rating these two people the same, or these group of people the same? Are they coming to the same conclusions? And as we can see, if they come to the same conclusion, then the numbers on the diagonal should be the same. The 75, 4, and 10 should be very high, and the ones off diagonal should be low because that's a disagreement. So on the diagonal, they agree. On the non-diagonal, then they disagree. So is it enough? We're interested in knowing, is this enough of a departure to say that the two raters are getting different kinds of answers? All right, so let's read in this data called Kappa, and here we have rater 1, rater 2, and the weight of how many people they put into each category. So rater 1, basically this is in row in cell 1-1 is a 75, in cell 1-2 is a 1, in cell 1-3 is a 4. That's 75-1-4. Again, we can go back to the data and see where that 75-1-4 came from. And same thing for rater 2 or in rater for with the same raters for all cells in this analysis. All right, so how do we analyze this? We use PROC FREQ, and again, we're looking at rater 1 by rater 2, and in this case, we're using the option called agree, and also a second statement called test Kappa. And these two are used to test the analysis that we've been discussing. So let's look at the results of this analysis. So first of all, we find the value called Kappa, and that's the primary statistic of interest. And this is the way we interpret Kappa. This is a table that is commonly used here. So notice we get a 0.6765, and we're interested in, what it's measuring is whether or not we have agreement between the two raters. And so we look at the Kappa value in the interpretation table, and we go down to where it would fall on, so it's the one that's 0.61 to 0.8, and we see that that is a substantial agreement. Now this is quite different from looking for a p-value and things like that, which is measured in some way, and I'm not going into that. The text has additional explanation for these results. I just want to show you how you would then measure the Kappa and then how you would interpret it. All right, there's also another way of calculating Kappa, and that's called a weighted Kappa. In the previous case, the categories that we were looking at were non-ordered. That is, the psychology, neurological, organic, those that had no order to them. But sometimes our categories do have a meaningful order to them. And in that case, we have to do a slightly different Kappa test called the weighted Kappa. For instance, in a test of recognition of potentially dangerous airline passengers, suppose a procedure is devised that classifies passengers into three categories. 1 is no threat, 2 is of a concern, and 3 is a potential threat. So now we see that the three ways that we're classifying individuals now has an order to them rather than the previous example where it had no order. So here is the data, for instance, we're looking at, and we see that each row is a passenger, and we have two raters or rating systems, and each one of them is rating this passenger. Now the first several are all rated 1. However, number 5, rater 1 rates it a no threat, but rater 2 rates it as a threat. So here we have a difference. So we're interested in knowing how these two rating systems differs, if they're consistent or maybe not consistent. So the way we would analyze this is, again, using PROC FREQ. We read in the data called security, which we just looked at, and the table is rater 1 by rater 2 / agree, which was the same as last time, and then semicolon, and then this time we say test WTKAP, weighted Kappa. And so here are the tabled results of this analysis. And again, we're looking, if we look at the rows that are the same, like 1, 1, 2, 2, 3, 3, those should be the high numbers, 58, 24, and 4. And then the ones off of this diagonal should be low. And so we're interested again in knowing, is there a consistency here, or is the two raters or rating systems not getting the same answer enough? All right, so we run the analysis, and again, there's a number of tables displayed that I'm not talking about. I'm just going to focus in on the weighted kappa. And you can see here the weighted kappa is 0.7413. For this analysis, that's the value we're interested in. We can use the same interpretation of the kappa table as before, and this would be a somewhat of a substantial agreement. So we see that most of the time they agree. Now, again, there's some other issues going on here, and that is if the agreement has a potentially extreme result to it, like a disaster on an airplane, maybe this is not high enough of an agreement. So we may want to look at that again. But see the text for additional interpretation of this result. All right, so that concludes this chapter discussing various ways to use PROC FREQ in analyzing one- and two-way tables and looking at measures of risk and inter-rater reliability. Next time we'll be comparing means using the t-test. I hope you got something out of this tutorial. If you did, if you would subscribe and like this channel, we'd appreciate it. Thanks for watching.